Hello, in this video we're going to discuss the idea of continuity. And you may already have an intuitive sense of what continuity is. It's something that you can draw continuously. Well, it sort of defines itself. So maybe a better way to say it is a continuous function is one that we can draw without lifting your pencil or piece of chalk. So this is what a continuous function looks like intuitively. But first, let's discuss what we mean by continuity at a point. Well, the idea of continuity at a point is that you could draw the graph around that point without lifting up your piece of chalk. So for example, I have this picture here. Notice I can start here at -2 and I can go, but when I get to -1, I have to pick up my piece of chalk. So we'll say this is not continuous at -1. Keep going, keep going, keep going, keep going, keep going. There's a hole in the graph. I have to pick my piece of chalk up. Keep going, keep going, keep going, keep going. There's a hole that suddenly jumps down here. Again, I have to pick up my piece of chalk. Keep going, keep going, keep going. Nothing there. So therefore, you'll notice that I had problems at -1 where I had to pick up my chalk, at 1 where there's nothing there, and at 2 and 3 where there's holes in the graph. So looking for holes in the graph or jumps are probably your big tip-off. Mathematically, this can be expressed quite simply as a function f of x is continuous, and I usually use the abbreviation for continuous. I usually use CTS at a point C if, and here it is, the limits as x approaches C of f of x equals f of C. So if the limit as you approach the point is equal to the value at that point, we say it's continuous. Now this is actually 3 statements in one. The first statement is that this limit exists. And as we discussed in previous sections, the limit existing means the limit is the same from the left as it is from the right. So the limit has to exist, the function value has to exist, and they have to be equal to each other. So this is actually 3 requirements in one. This side makes sense, this side makes sense, and they're equal to each other. So let's go back over here. So we'll notice that this guy is not continuous at x equals -1. And we can see that because there's a jump. Well, if there's a jump, that means the limit as x approaches -1 of f of x does not exist. This limit does not exist. Therefore, the left-hand side of this does not make any sense. It's also not continuous at 1, and that's because there's a hole in the graph, and that is simply that f of 1 does not exist. There is no f of 1. There is no value for this function at 1. We can also say, there's a problem at x equals 2. Well, in this case, the limit as x approaches 2 of f of x, the limit, which of course doesn't care about the actual point, it cares about nearby, the limit here is 1. However, f of 2 is 0. So notice that in this case, the limit does exist and the value exists, but they're not the same thing. So this is also not continuous at 2. And now we're left with 2 special cases I'd like to address, which are these endpoints. If you're looking at a function on its domain, and this function only has domain from -2 to +3, we allow the endpoints a little bit of flexibility there. We're going to say that this guy is continuous at -2 because the limit from the right-hand side equals the value of the function. However, we'll say it's not continuous at +3 because the function is not defined there. So we will say it is continuous at x equals -2, since the limit as x approaches 2 from the, -2, from the positive side, that negative doesn't show, I'll try it again. There we go. This guy, the limit, equals the value of the function, but not at x equals 3, since f of 3 does not exist. So this is just one little small caveat. If you're talking about the endpoints of the domain, you only have to worry about the direction from which the limit even makes sense. So we will say this is continuous at -2, since the limit from the direction the only direction we can possibly approach it from. There's nothing on this side, so there's no limit to talk about. So if you're talking about endpoints, as long as the direction you're coming from, you need the limit to equal the value of the function. Of course, that fails at 3 because f of 3 does not exist. So we will say that it's not continuous at -1 because the limit does not exist. You can tell that's a jump. It's not continuous at 1 or 2 because there are holes in the graph, which means that if there's a hole in the graph, that means here f of 1 doesn't exist. Here f of 2 exists, but it's in the wrong place. And then finally, the special caveat at the endpoints. This guy is considered continuous because the limit from the only direction that makes sense to talk about does equal the value of the function. This, on the other hand, does not, because the value of the function is not defined. Well, now that we've considered a graphical example, let's consider some algebraic examples. So the first one, the directions we're going to go for determining where the following functions are continuous. And really the secret to figuring out where something is continuous is to ask, what is its domain? And then to ask, where is it not continuous? Well, and then once you know where it's not continuous, you can work backwards to figure out where it is continuous. All right, so the domain of this guy is going to be from -3 to 3. Because you can plug any number you want in between -3 and +3. If you're trying to plug in 3.1, though, you're taking the square root of a negative number. You're trying to plug in -4, you're taking the square root of -7. Things like that. So therefore, we know that the domain is from -3 to +3. Now, this is our domain. Those are the numbers we can plug in. And really, the thing to look out for here is, are there any jumps or holes in the graph? Well, if we looked at the graph, it looks like a semicircle. And you might not know that right away, but really, always look out for where there are holes in the graph. That's usually some kind of piecewise thing, or where there's going to be some kind of division by 0, or there's going to be some kind of negative square root thing, but a lot of that's ruled out by the domain. So really, what you want to look for is the domain, and then just figure out where might there be danger points, where the piecewise functions changing gears. Well, in this case, it's everywhere. That makes sense. So therefore, this guy is considered continuous on -3 to +3. And yes, I can include those endpoints because the value of the function is 0 there, and the limit from this direction is 0. The limit from this direction is 0. And of course, at the endpoints, we only care about the limit from the direction that makes sense. Next, we're going to consider our friend x over the absolute value of x. We talked about this one last time. Of course, its domain is that x cannot equal 0 because you cannot divide by 0. All right? But besides the point 0, as we determined last time, this function is just equal to -1 if x is negative and +1 if x is positive. So the only place it doesn't jump is here at 0. So we'll say that this guy is continuous from -infinity to 0 and then from 0 to infinity. Notice here I had to use parentheses because you can't plug in negative infinity. It's not actually a number. And you can't plug in 0 because it's not in the domain. For our last one, again, we're going to look at its domain. Its domain is that x cannot equal 5 because that requires division by 0. And this graph looks something like this guy with an asymptote. And so again, this guy is quite easily continuous from negative infinity to negative 5. I'm sorry, positive 5, and then 5 to infinity. So in cases where it's just a single function, it's usually pretty easy. The answer is it's continuous on its domain. This guy's continuous where it makes sense. This guy's continuous where it makes sense. This guy's continuous where it makes sense. Let's consider an example where it's not just immediately the same thing as the domain. So now I'd like to consider f of x given by a piecewise function. And if x is less than 0, it's going to follow the rule x plus 1 over x squared minus 1. If x is bigger than 0 or equal to 0, it's going to follow the rule x plus 2. And we want to figure out where this guy is continuous. Well, the first thing to notice, of course, is our domain. X, according to this rule right here, x cannot equal negative 1. Because if you try to plug negative 1 into the bottom, that's going to be a problem. Notice I don't have to worry about x equaling 1, because if x equals 1, I follow this rule. And this rule has no kind of problems at 1. However, notice I cannot plug in negative 1, because negative 1 will make this be undefined because it requires division by 0. However, 1, we use this rule, so don't worry about it. All right, so we've got, the first thing we thought about is the domain. X better not equal negative 1. The other big tip-off is the fact that we're switching gears here at 0. And so the only possible trouble point in the domain is x equals 0. And so the question is it continuous at x equals 0? Well, the only way to figure that out is to ask ourselves the limit as x approaches 0 of f of x. Is this the same thing as f of 0? Well, let's knock out the right-hand side real quickly. F of 0, all right, so if x equals 0, I use this rule. So let's see, I plug 0, 2. All right, so we've got the right-hand side, f of 0. That's easy. Now let's talk about the left-hand side. Well, the left-hand side, the issue we're going to run into is the fact that there's two rules. There's one rule if we're using something less than 0, and there's a different rule if we're using something bigger than 0. If it's less than 0, we use this rule. If it's bigger than 0, we use this rule. All right, so if it's less than 0, we use this rule. And we're basically just going to try to see what happens when we plug 0 in. We're going to get 1 over negative 1. This equals negative 1. On the other hand, when we try to plug it into here, the limit when we deal with this part is 2. Therefore, the left-hand side of this guy does not exist. Does not exist equal the number 2? No, because 2 is a number, and does not exist means that there is no number. So therefore, this guy is not continuous at 0. So our final answer will be, where is this guy continuous? It's continuous from negative infinity to negative 1, because negative 1's not in the domain. And then it's continuous from negative 1 to 0. and then it's continuous from 0 to infinity. So, in order to figure out where a function is continuous, ask yourself where it's not continuous. And the big places to look for are places that are not in the domain, because if it's not in the domain, how can it possibly be continuous there? The right-hand side can't possibly make sense if this number's not in the domain. There is no f of -1. So if I try to do the same process with -1, the right-hand side wouldn't make sense. The other thing to look out for is where the piecewise function changes gears. It's got one rule for numbers less than 0. It's got a different rule for numbers bigger than 0. It's changing gears. We have to check at that point. Now, it is, of course, possible that this limit could exist and just not equal this number, or it's possible this limit could exist and it equals this number. So it all comes back to this equation right here. You want to verify, is this true or not? If this side makes sense, which means both these limits make sense and equal the same number, and also if that equals this third number, then you know that it's continuous at that point. In this case, these are not equal to each other, therefore it is not continuous at 0. In general, a function is considered to be continuous if it is continuous at every point in its domain. So previously we were saying, at what x's is this continuous? Now we're just saying it's continuous as long as it's continuous at every place it makes sense. So for example, f of x is the square root of 9 minus x squared is continuous on -3 to 3. Therefore, we'll say it's continuous in general because it is continuous everywhere in its domain. As is g of x, it is also considered a continuous function. It's not continuous at 0, but 0 is not in the domain. Similarly, our h of x, 1 over x minus 5, is also continuous on its domain because the 5 is automatically excluded by the domain. And then finally, our f of x our capital F of x is not continuous since not continuous at x equals 0, which in this case is in the domain. Fortunately for us, continuity primarily follows the limit laws. So that's to say if f of x and g of x are both continuous at some point c, so if they're both continuous at that point, then the following functions are also continuous. F plus g, well if f is continuous and g is continuous, if you add them together, it's still continuous. Subtraction, if you multiply everything in f by 3, it stays continuous. It just makes everything 3 times bigger. F times g, f divided by g, as long as, of course, g of c does not equal 0, because there's no dividing by 0, of course. And of course, also f of x to a power. So really, once you have your initial points, you can add things, subtract things, multiply things, power things, root things, divide things, whatever you have to do. So that actually gives us a list of continuous functions. Okay, so first of all, polynomials are continuous. Those are things of the form like 3x to the 5th minus 7x squared plus 2. I don't know, things like that. Notice that all the powers are integers. And notice that all you've done is you've multiplied 3 times x to a power. Well, x is a continuous function. Raising it to a power stays continuous. Multiplying by 3 keeps it continuous. 7x squared. X is continuous. Squaring it's continuous. Multiplying by 7 keeps it continuous. And then taking one and subtracting the other keeps it continuous. So polynomials are continuous. So are trig functions on their domain, mind you. So sine of x and cosine of x have domains everything and are therefore continuous everywhere. I will point out that secant of x and tangent of x are continuous as long as x does not equal pi over 2, because you can't divide by 0, because it's secant and tangent, the cosine's in the bottom, that will require division by 0. And then I'm going to put plus pi n. And what this means is that you can take pi over 2 and you can add 1 pi to it, or 2 pi's to it, or 3 pi's to it, or you can subtract 7 pi's. These are exactly the points where cosine equals 0, and therefore this guy is going to be undefined. And then similarly, cosecant of x and cotangent of x are continuous except where x is a multiple of pi. For example, at 0, that will require division by 0. At pi, requires division by 0. At negative 17 pi, requires division by 0. So, trig functions are continuous in their domain. Sine and cosine are continuous everywhere, because sine and cosine can handle any number. There's no division by 0. These guys are continuous as long as you're not talking about the points where things go completely crazy, requiring division by 0. We also have, tack on here, exponentials are continuous everywhere. Logarithms are continuous as long as the stuff on the inside is positive, because we're not allowed to take the ln of 0 or a negative number. And all of this information is very neatly stored in Theorem 8 on page 88 of your textbook. Fortunately for us, in calculus, we almost work exclusively with continuous functions. And that is because the derivative, the main topic of this course, requires continuity. Well, if we're going to do the main topic of this course, continuity is a prerequisite, then almost all the functions we deal with are going to be continuous. So keep in mind, if you're looking for continuity, make sure you check your domain, no division by 0, no square roots of negative numbers, no ln's of 0 or negative numbers, and then just check where there's some kind of piecewise jump. But besides that, almost all the functions we're ever going to see are going to be continuous. In our next video, we'll talk about why continuity is so useful. See you in class.